So this is going to be a video about finding the inverses of 2 by 2 matrices. Now there's a couple of things you need to know before I do this. First of all, you're not going to be expected to find the inverses of matrices that are larger than 2 by 2s by hand. If you ever need to find inverses of those kinds of matrices, you'll be allowed to use technology in this class. The second thing that you need to know is that only square matrices in general have inverses. So we'll only be taking inverses of square matrices. Makes sense. So before we go into this, I need to remind you what an inverse actually is in this context. So if you remember the numbers 3 and 1/3, we call them reciprocals. That's what we tend to call them. There's another name for that though. They're also called multiplicative inverses. And they're called multiplicative inverses because when you multiply 3 times 1/3, you get 1, which is what's called the multiplicative identity. Now remember, we talked about identity. A multiplicative identity means it's what you would multiply any number by to get the same number back. So with regular numbers, the multiplicative identity is 1. So something times its multiplicative inverse gives you the multiplicative identity, and that's true in any system. Now, this is the system of numbers where the multiplicative identity is reciprocal and multiplicative inverse is reciprocal and the multiplicative identity is 1. But in matrices, it's a little bit different. So what we're going to do here is figure out what a multiplicative inverse looks like in matrices. So we have this matrix here, it's a 2 by 2. And we're going to multiply it by its inverse, which we don't know the size of just yet. And because it's an inverse, when we multiply it by that, we should get the multiplicative identity back. So if you remember how identity matrices work, they're always square. They have 1s down the main diagonal and 0s everywhere else. Well, since I'm starting with a 2 by 2 matrix, that means my outer dimensions, in order for this multiplication to work, would have to give me a 2 as the second dimension here. And then, since identity matrices are square, this would have to be a 2 by 2. So basically I'm looking at the 1, 0, 0, 1 matrix. Now, I don't know what the inverse is though, and that's what I'm trying to find. Now what I'm looking for here is not a proof of what the inverse formula is. I'm going to do an inverse of this matrix and I'm going to look for patterns, and then we're going to talk about how the patterns actually apply. So I don't know what numbers go in the inverse matrix, but I do know this has to be a 2 by 2. Inner dimensions have to match. Outer dimensions give the answer, which is the identity. So I'm going to fill this with letters. Now, I know it looks intimidating. It won't be that bad once we get into it. Trust me. So I've got 2 matrices multiplied together here that equal the identity. So what I'm going to do is I'm going to take these 2 matrices here and I'm going to multiply them together. So I can have one matrix on each side of the equation and then talk about how those things relate to each other. So my answer to this multiplication would be a 2 by 2. And if I looked at row 1, column 1, row 1, first matrix, 7, 5, column 1, second matrix, A, C, multiply, and add. So 7A plus 5C goes in row 1, column 1. Now I can do the same thing on each of the other blanks. Row 1, column 2, 7B, 5D added together. Row 2, column 1, 2A, 3C added together. Row 2, column 2, 2B, 3D added together. All right, so that's the multiplication of those 2 matrices. And that matrix has to equal, according to this equation that we wrote up here, the identity matrix. Now, if you look at these 2 matrices, they're both 2 by 2s, right? And this equation says that they're equal to each other. Well, in order for matrices to be equal to each other, they have to have the same dimensions, which these do, and they also have to have corresponding elements equal to each other. Remember, the placement in a matrix is really important to the meaning of the number in the matrix. So you can't just go willy-nilly switching numbers around in the matrix. So each of these things is equal to its corresponding element. So what I'm going to do then is take that and write it out. 7A plus 5C, which is in row 1, column 1, has to equal the 1 in row 1, Likewise, 7b plus 5d has to equal 0. 2a plus 3c has to equal 0. 2b plus 3d has to equal 1. So if you look at what we've gotten when we set those corresponding elements equal to each other, we've got two systems of equations, each in two variables. So I'm going to take those and I'm going to solve them for their corresponding, their variables. So let's see, I'll take this first equation and I'll do elimination. Let's get rid of the a's. How about 14a plus 10c equals 2? And then negative 14a minus 21c equals 0. So that gives me negative 11c equals 2. So c is negative 2 over 11. And then I can take that negative 2 over 11 and plug it back in. So that's 3 times negative 2 over 11 equals 0. So that's negative 6 elevenths. If I move it to the other side, that'd be 2a equals 6 elevenths. A is 3 elevenths. Yeah, I know, these numbers are ugly. and this is a little tedious feeling, but don't worry. You're not going to have to do this every time. Remember, we're trying to come up with a pattern so we can actually write a formula, so you don't have to do this every time. So let's solve this other system. We're going to get rid of the, let's get rid of the b's. Multiply the top thing by 2. And that gives me that. Multiply the bottom thing by negative 7. And then add those equations together. So that will give me d as 7 elevenths. And then I'm going to take that 7 elevenths and plug it back in. So let's see, 7b plus 5 times 7 elevenths equals 0. So that's 35 elevenths. So 7b is negative 35 elevenths when I subtract it to the other side. So b is negative 5 elevenths. Okay, so I've got these numbers, this A, B, C, and D, and these are the elements in the inverse of that original matrix. So what I'm going to do is I'm going to write the original matrix down, and then I'm going to write the inverse matrix down, and we're going to look at patterns and what we get. All right, so original matrix was 7, 5, 2, 3. All right, so this is my original matrix. Let's call that matrix M. And then my inverse matrix, which the symbol for inverse in math is always, and looks like a negative 1 power. It doesn't really mean a negative 1 power here. It means the inverse of this matrix. We've got, let's see, A was 3 elevenths. B was negative 5 elevenths. C was negative 2 elevenths. And D was 7 elevenths. Now, I'm sure you look at this and you see immediately there's a common factor in every single one of these terms, and it's 1/11. Now, remember how scalar multiplication works in matrices? That if you're multiplying a matrix by a number, you distribute it out to each of the numbers? Well, we're going to do the opposite. We're going to take something that's a common factor in everything and pull it out in front as a scalar. So I can write that 1/11 out in front, and that would leave me behind 3, negative 5, negative 2, and 7. Now, look at this. We've got this original matrix that was 7, 5, 2, 3, and we've got this inverse matrix that has sort of the same numbers, but some things have gone on. First of all, I want you to notice that the number in the top right, try it again, the top left and the bottom right, the 7 and the 3, they switched places. The 3 went to the top left, and the 7 went to the bottom right. And I want you to look at the other two numbers, the one on the top right and the bottom left. 5 and 2 became negative 5 and negative 2. They changed sign. And it turns out every single time you're doing one of these 2 by 2 inverses, this happens. The top left and the bottom right numbers switch locations, and the top right and the bottom left numbers change signs. So the only question that we have is, where does 1/11 come from? Well, if you look at the original matrix, and instead of looking at it as a matrix, you look at it as a determinant. 7 times 3 is 21, minus 2 times 5 is 10. It's 11, which is the denominator of that fraction. So it has to do with the determinant of the original matrix. So what we have now is a pattern, and this pattern holds for every single 2 by 2 matrix. That if we want to find the inverse of a 2 by 2 matrix, it's a 3-step process. First of all, you find the determinant of that matrix, and then you put that under 1. So 1 over the determinant of A. That was that number that ended up being a common factor in everything, right? Times the matrix that you get when you switch the top left and bottom right and change the signs on top right and bottom left. And this is a formula for the inverse of a 2 by 2. Now there are formulas for the inverses of 3 by 3s and 4 by 4s. Totally not going to make you memorize that or do it by hand. This is the only one that you'll be expected to do by hand. The others you'll be expected to do with technology. Stop recording.